So one of the questions was, if we set up these force balance equations for trusses, can we reliably expect to get a single unique solution? Well, thank goodness we have linear algebra in our back pocket. So if we look, I know not everyone feels that way, but in this case you'll like it because it's a very simple approach. Let me just go back to our truss back here. This is one of the sample trusses, and this system of setting up force balance equations worked for it. We got a perfectly unique answer that gave us the force distribution in the beams. We had 7 beams, F1 through 7, and we also had 1, 2, 3, 4, 5 joints. So how does that play itself out in terms of variables? Well, the unknown forces, the Fi's, if you like, are the unknowns. They're the variables. And we had 7 of those. And we also had, presumably, 7 equations. Well, where did we get 7 equations from? We had 7 equations because we had 5 joints times 2 equations each. 2 equations per joint. But then we got to throw some things away. So if we just had 5 joints, we'd be in trouble. We'd have 10 equations, 7 unknowns. But with the pin joint, the nice thing about the pin joint is the forces do not have to be in balance on the pin. Why? Because the pin always pushes back. The pin always resists any external forces. So that lost us 2 equations that we didn't need to satisfy. And fortunately, again, we also had 1 equation on the roller joint. The vertical forces were automatically in balance. We didn't have to balance them ourselves. So we ended up losing 3 equations from the pin and roller. And you'll notice that that equals 7. And linear algebra says, unless you really mess things up, 7 equations, 7 unknowns, you can expect in general, barring any linearly dependent rows and columns, you can expect to get a unique solution out. So this will work for this truss. And it did work for this truss. In general, can we rely on this? Well, thankfully, yes, if we have a certain structure to our truss. So it's all the stuff we just talked about there. In general, if we have B beams and N joints, so the beams are the unknowns, we're going to have 2n minus 3 equations. 2 times joints for horizontal and vertical. And we're going to have minus 3 for the pin and the roller. And we're going to have B beams forces that we need to find. Those are going to be the unknowns. If we get the same number here, so if B is equal to 2n minus 3, then we get what's called a determinate truss. And life is happy, life is good. We can solve the equations and get a unique answer. There's no ambiguities. We are only, in this class, going to deal with determinate trusses. So what do these look like? Are they the kinds of things you'd expect to come across in nature? Well, or in design? Absolutely. If we had anything that's basically built out of triangles in one single row that has 1, 2, 3, 4, 5, 6, 7, 8, 9 joints. Oops. 9 joints, which will lead to 2 times 9 minus 3, which is equal to 15 equations. And if we count the beams, do a quick count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm getting 15. Anyone getting a different number of beams? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hey, 15 beams. So we're going to have 15 unknown forces. So this will be determinate. So that gives us a lot of leeway. Anything that's sort of built out of triangles stuck side by side in a single layer is going to be determinate. What gets not determinate? Well, if we start putting weird cross members in, so if we do, here's a classic, this versus the cross bracing idea, the same version. This has 1, 2, 3, 4, 5 joints, which means 10. 2 times 5 minus 3 is 7 equations. and it has 1, 2, 3, 4, 5, 6, 7 beams. So that's okay. This guy, being exactly the same, has 5 joints, and so 7 equations. But it's going to have 8 beams. So I got 1 extra. And that is not determinate. Okay. So what do we like? We like these guys. These guys will have unique solutions we can work through. MATLAB will spit out the force balances. These ones will not, if we just do the naive way we did it right in the first method. Okay. Does anyone know what you do with indeterminate trusses? Like what machinery you have to pull out to deal with that case? Is this, show of hands, is this covered in 220 at all? Civil 220. Indeterminate trusses? Not at all. Okay. Let's just say it can be solved. What it turns out you have to deal with, and this is getting into way more physics than the non-engineers want to see, you actually have to look at how the stress and the strain, so how the force balance on that beam, will actually compress or stretch out that beam. So you're actually looking at the distortion of the physical layout. So you're pretending things move. That's a whole, it leads to actually a nice system of linear equations again, but it's a whole pile more algebra. So we're not going to look at that. It's doable. It's just more complicated than we need for the kinds of designs we're looking at in this course. So there is a solution, but not one we're going to cover in this class. It depends on how you construct it. Good question. That middle cross could be a joint, or it could be just 2 beams going one in front of the other. You'd have to be more careful about defining it. Even if you put a joint in there, though, it's still not going to be determinate, as it turns out. You'll get 1 more joint and 2 more beams, and it's not going to work out. So you'll still be off balance. Okay. So just the reason I'm saying this is because later on, for people who are choosing the project option on trusses, then this is going to be something you're going to encounter. Is you're going to want to build a non-determinate truss, and the math's not going to work. So trying to escort you away from that idea early on.